Hello and welcome to another Wolfram Institute live stream. Today we are pleased to have the YouTube content creator 2Swap, who's made several mathematical explanatory videos on the topics such as chaotic systems, fractals, gravity basins, and double pendulums. A video about lambda calculus with some very nice illustrations there. And the latest video, I really like the combinatorial, like multi-way graph of a state space of a block sliding game. Today, 2Swap will present on the strategy of Connect 4 and talk about some of the emergent structures that come out of the combinatorics of its states graph. 2Swap, go ahead.
Sweet. Yeah, I just want to say thanks to you, Dugan, and also James for inviting me. My name's Alex. I go by 2Swap Online. This is my YouTube channel. You can check it out if you want. So as Dugan already said, yeah, my topics mainly can like have to do with fractal dynamics and basically emergent systems in general. So for example, I've made a video about double pendulums. In the case of double pendulums, you have it's a very simple system. The differential equations behind it are pretty, well, I shouldn't say simple, but they're not too complicated that you can't understand what they're trying to explain. But you iterate them over time, and you get all of these different sort of behaviors depending on the initial conditions. In some cases, you get like chaotic behavior, which is in this picture here. That this is like the white stuff is the chaotic pendulums in a certain plane of the phase space of the double pendulum initial conditions. And in some conditions, you get coherent behavior where it's not sensitive to perturbations and things like that. So you have this difference in phase as a result of sort of some of the complexities of this differential equation. I also talked about the Mandelbrot set, classic fractal. I talked about basically what happens if you have a object that is falling in the gravitational fields of multiple planets. You get these complicated images like this. All cases of like emergent structure. You take a system, you like have some simple rules, you iterate them, and over time you get this complexity that emerges out of them. And the last video that Dugan was just mentioning is about graphs of the state space of puzzles sort of like this one, like these sliding blocks. They define a graph, and you end up getting a whole bunch of cool like topological properties where locally you see like sometimes it approximates like a Euclidean manifold. You get like a grid, but on the whole you get these much more complicated structures as a result of sort of the points at which different small topologies sort of connect with each other, and you end up with these much more complex structures as a whole. Cool. So today I'm going to be talking about Connect 4. So just in case anybody doesn't know, the idea is like we have a 6x7 grid, 7 wide, 6 tall, and the players are dropping pieces from the top, sort of like in this picture. And the goal is to make 4 in a row, either diagonally, vertically, horizontally. The game is simple, and we're going to see exactly like with all those other systems, you get all sorts of very cool emergent properties that come out of it. So just before we get started, a little bit of a background of the game itself. So first of all, I'm just going to be using the convention of red goes first. So I usually use red synonymously with player one. So that's what I mean if I say red should win under optimal play. And that is indeed the case. Red does win under optimal play. So if you're player one and you play in the center on the first move, theoretically you should win if you play optimally after that. It turns out that if you go one over to the side, it's a tie under optimal play. And if you play in either of these two columns, you should lose under optimal play. So the only correct first move is to go in the center. So this is a pretty big object, right? There's a lot of positions that you can get to. In terms of just like the amount of different nodes at each, like at n plies from the starting position, like there's one empty board. There's 7 places that you can place the first spot. 49 after that, and it just grows exponentially thereon. You'll notice it's not perfectly like 7 to the n because of what's called transpositions. You can sort of take 2 different paths to get to the same spot. For example, if red plays like the first column and then the second column on red's 2 consecutive first moves, that's the same as going like the second column then the first column. So you don't get a perfect exponential curve here, and eventually, like, of course, the board fills up, and that yields a total amount of nodes in this theoretical complete graph of 4 trillion. So that's a lot of that's a big structure. It's not incomprehensibly big, and this is one of the reasons that I focus on Connect 4 a lot, is because it's big enough to have a lot of emergent behavior, but also small enough that, like, with modern compute, you can start to reason about the structure of these objects. So just a quick little history of the game and computational study into the game. It was first solved in 1988. When I say solved, I mean a weak solution, and I'll explain exactly what I mean by that in a few slides. But this is the first time someone figured out that precisely what I just said, that player one should win under optimal play. So that was solved first by James Dow Allen, who published a textbook on the game. But also, I think his solution is not very well attested online. I couldn't find many details about it. But there's a paper by Victor Alice, who published at the University of Amsterdam just 15 days later, and it's very well documented what he did and how he solved the game. Yeah, after that, there was sort of the next sort of goal, I guess, after solving it weakly, is to solve it strongly, which I will explain the details of momentarily. But the idea here is, basically, you want to document, for each of those 4 trillion nodes, what exactly is the optimal result? Like, what should happen under optimal play? Will it be a tie? Will it be red who wins? Will it be yellow who wins? So I think way back when, due to just like computational, sort of just like storage requirements and things, I don't think that was quite possible. But what John Tromp did was he made a complete table for 8 ply positions. So that means like all positions that are a distance 8 from the start, and documented what the optimal result was of all of those positions. So that was solved after the weak solution happened. And this is just an example of me running 4 stones on my own desktop. That's his published tool, which is now used as a CPU benchmark for. And it's sort of, I think it's sort of the state of the art Connect 4 engine, and I used it a lot in my own research as well. And nowadays there's like a modern online like web browser application that you can use, and you can just like, play out a position and it'll tell you exactly what the optimal next move is. And just 2 years ago, someone finally did the full strong solution of actually documenting every single position and writing it to a single file on, presumably on some like NAS server or something somewhere, because it took a total of 15 terabytes or 16 terabytes, I guess, rounding up. So it's a pretty big object, is this full strong solution of Connect 4. Now, all of the solutions that I've mentioned so far they're not, you can't really understand what they're doing, right? In all of the cases, they're kind of you give it a position, it tells you what the optimal result is. There's no further intuition into what the structure of that solution looks like, with a small exception of Alice's paper. He ended up proving some things about a number of positions in the game that he proved some rules that can be used to sort of mathematically confirm whether a node is white to win or black, or sorry, red to win or yellow to win. In his terminology, white or black. But in general, we don't get a sense of the structure of this solution. We can't see what the variations look like. We can't. There's no visual way to intuit what's going on under the hood. So that was sort of my goal, is like, can we do exactly that? Can we make a strategy, a weak solution to Connect 4, that is perhaps human memorizable, perhaps something that we can visualize entirely? And I'll just go ahead and spoil the answer up front. As for visualizable, the answer is an absolute yes, and that's what I have right here. This is a complete graph of a weak solution of Connect 4. And whether it's human memorizable or not, I will leave for debate. But it's 9,800 nodes, which is much more plausible than anything else I'm aware of. I'll put it that way. And it also has some extra sort of bonus features. Thinking of it as a program that we can run to like return an optimal Connect 4 move. there's no search invoked. There's no like unbounded computation that has to be exerted. It's quick is the point. And all we need is this small opening book, which is what you're looking at here. Okay, so I talked about strong solutions and weak solutions. So what are those? A strong solution is just an exhaustive list of every node and an annotation of like whether it's red to win or yellow to win or tie. Because you can tie, the whole board can fill up without someone connecting for. So that's what a strong solution is. You have just this entire list of every single position and what should happen under optimal play. A weak solution, and this is just a graph of all of the nodes up to a depth of 4 ply, right? So this is up to 4 moves. This is the graph of the game. A weak solution, on the other hand, is a dictionary of enough positions with annotations that can guarantee you as player 1 a win. So in the case of Connect 4, I mentioned, the center column is the best place to go. So there's no point in really memorizing what happens if you start off center, because like you would never do that in practice. So that's redundant information. You don't care. You don't need to know that to be able to guarantee a win every time. So if our goal is to create this program that plays optimal Connect 4, we don't need to worry about such variations. Yeah, we don't need to include other openings of the game. A property of this weak solution graph is that for any red to move node, you're only ever going to need to choose one outgoing edge, right? There's no point also in like memorizing 2 variations from the same starting point. Whereas compare that to the yellow to move nodes, we have to include every single edge, right? Because yellow could do whatever adversarial trick they want to, and we have to account for all of that. We have to know what to do in any possible continuation of what yellow decides to adversarially throw at us. So of course, a weak solution could, in theory, have multiple edges outgoing from a red node, but like for our purposes, insofar as we're trying to define this as simple as possible program to play the game, that would be unnecessary. Okay, so another thing about weak solutions is they're not unique. So there is a bit of creative, how do I say it? Creative, you can make choices when you're constructing the weak solution. So for example, I mentioned this was red to win. So in theory, like, of course, this is still red to win because yellow, it shouldn't matter what yellow does. Now in this position, it turns out there are 2 correct continuations, being this column and this column. By the way, you can see my mouse, right?
Yeah, we can see it.
Cool. So like we can choose which of these 2 variations we want to contain in our weak solution. There's not, it's not forced upon us, right? In practice, it's generally accepted among Connect 4 players that this is the easier variation. And I'll talk a little bit more about how design decisions like that factored into the approach that I ended up using. But in general, the idea here is that a strong solution is a full documentation of the game. The weak solution is not. The weak solution is a guide to how to play correctly, whereas the strong solution is a full dictionary. And with the extra benefit, we'll use it as a benefit in our case, that we can exert this creative choice when we're creating a weak solution. So that's our goal. We're gonna make a weak solution to Connect 4 that is small. Okay, so how would you do that? Let's just say you're showing up at a Connect 4 tournament. How do you play? What are you going to do to guarantee perfect play? Like your first strategy might just be to like you show up there and you just read the whole game out in your head. Like I have memorized the C code and compiled it in my mind of 4 stones, and I'm just going to run that program in my head like when I get to the tournament. Of course, that takes forever. There's no practical way that any human's ever going to do that. Alternatively, we could go in knowing an entire like DFS tree of the whole game. We can memorize everything up front, have this tree in our mind when we show up, and we just query that hash map. Like we get there, we see the board, we query our mental model of the game, and from there we just play in accordance with that mental model. There's sort of a balance here, right? We're balancing the runtime compute that we're executing with the memorized upfront knowledge that we have. So these 2 strategies sort of exist at opposite ends of this spectrum, right? And we can balance between the 2. You can think of Oh, before I talk about, you know, some other strategies, these two strategies are kind of the same thing insofar as the like data structure that we're mentally interfacing with is the same object. The only difference is that like in the case of B, in the case of where we memorize everything, it exists in memory, but in A, we're building it on the stack in real time and evaluating that tree through like minimax or through alpha beta or something like that. So it's the same object. We're still talking about the same data structure. It's just where is it? Does it exist in one place in time, or are we programmatically iterating over this tree? And so there's sort of a balance to be struck here, right? You can take the approach of like think about everything up front and like don't memorize anything versus memorize everything and don't think at all, right? And if you look at it this way, there's a rather like this is a hint that there's a kind of nice middle point where sort of uh, you can sort of memorize like halfway through the game, sort of as John Tromp did with his quote unquote strong solution, is memorize 8-ply, all the variations, and then execute a much, much smaller search on the fly and read the whole game out to the end. We can do better though. This talk is about how we can do something much, much more clever than quite that. So just as a motivating example, here's a Connect 4 puzzle, and see if you can think of how red can play and win. I promise you that this is indeed red to play and win. It's tricky, but I'll give you the opportunity to think about it a little bit. Any ideas? Anything you notice?
Yeah, there's a threat for red in the center column.
Bingo.
The
Yeah.
third peg. And
yeah, exactly. Yeah.
so you kind of want to force yellow to put something there so that you can get to it.
That's exactly right. Anybody else want to chime in before I start to explain? Okay, so the idea here is like you'll notice that first of all, it's red to play. So theoretically, if the entire board fills up with the exception of this center column, if red plays here, then it's yellow, red, yellow, red, yellow, red, all the way through, because these are each an even amount of spots after red plays here, right? So we can imagine red. We can imagine red starts by playing in this spot. Then all of the columns, with the exception of the middle, has an even amount of spaces left.
It's just showing a red play icon.
Oops.
There we go. All right.
Is that better?
Yeah, we're back.
Cool. So yeah, if red plays here, then each column has an even amount of spots. So what red could in theory do is just continue right after what yellow did on each column. We'll see that in a second. I forgot I was going to ask you what the weak solution to this should look like, and I have two examples here of graphs. Do you think it might look like this, or do you think it might look like? Hold on. Do you think it might look like this? I somewhat spoiled the answer there a little bit.
I'm going to guess the second one because it seems like there's some even odd sequencing kind of idea there.
Yeah, so you think it's very regular. Anyone think it's the left one? I did somewhat spoil the answer, but not entirely. It's actually a trick question. These are both weak solutions. Remember, we can exert creative choice. So
is this from the position we were just looking at, or is this from
this is the actual position we were just looking at. These two solutions are both graphs of the weak position, or of weak solutions, two different weak solutions of the position that we were just looking at. This is the rather naive solution of basically read it out and just play whichever is the leftmost column that is winning at any given position. This one is the strategy that I just described. So the point here is like there are some weak solutions of certain positions that have a lot of self-similarity and a lot of regular structure. And the idea here is that we can capitalize on precisely that property. if we can identify these regular weak solutions within the continuations of our connect 4 positions, then we can basically skip the compute step, right? We can sort of have our cake and eat it too, in where we memorize a small opening book, but then we don't have to do any compute after the fact. If we can somehow know a priori like that this is a position that has a very simple program to continue play with. So, okay, I sort of already explained this, but like red's going to go here. Now you have an even amount of spots on every column. There's this thread on the center column, which is on an odd row, which is exactly where red should land had this been the last column to fill up. And then like, assuming yellow plays anywhere, we can just play immediately on top of it. And then we know that the entire board will look like this before yellow plays in the center. And you'll see here that nowhere that yellow ever plays is there ever a line of 4. This is also the case for red, but we don't care. We're gonna make our connect 4 on the center column anyway. So then the game ends and we win. So that's all that we do. We play right on top of our opponent. It turns out to be helpful. I won't go into the details of why, but it turns out to be somewhat helpful to conceptualize this as two somewhat different strategies going on here, in the sense of on these outer edges, we're going to call that claim even. This is a term that was originally invented by Victor Alice in his paper, but we just use it to describe this strategy of play as red. Like if I'm the person that's playing the claim even strategy and I'm red in this case, we're playing on the even rows. So this is row 2, this is row 4, this is row 6. So we're going to claim the even rows and not play on the odd rows. This, of course, exhibits the exact same behavior as just playing on top of your opponent, with the exception of in the center column. On the center column, we're doing the opposite of that. We're claiming odd. We're claiming the odd rows. And so I came up with this notation. I call this a steady state diagram. And this is basically describing what I just said. The blank space, you can think of claim even as sort of a default behavior. So claim even is just notated as a blank space. Claim odd, I notate it as just a vertical bar. So this is sort of a cheat sheet. You can think of this diagram as a cheat sheet insofar as I can hand you this diagram. Like if you have this position in mind, I can hand you this diagram and it tells you exactly what to do to continue perfect play on this board. And that is exactly the strategy that yields that graph that I showed a minute ago.
And that's play on top of the other player until like it's filled up.
For the empty spaces, you are claiming it if it's even and ignoring it if it's odd. So for example, in this position, it's yellow to move, but if it were red to move, like this would be telling us to do nothing, because like, you know, red doesn't want to play on the odd row. Red doesn't want to play on row 1 or row 5 or row 3. So this empty space is saying, you know, if you're like, as the game continues, like if yellow plays here, we suddenly want to play on this spot, right? Because this is a claim even box on an even row. So we want to take this spot. Does that make sense?
Wait, I'm sorry, is it red to move from this position, or is it yellow to move?
From this position, red just played here, so it's yellow to move now.
Red just played there, okay.
Yeah, so yellow moves. I was saying in the hypothetical, if it was red to move, like none of this is telling us to do anything, because like these are all of the open spots are on odd rows for the claim even spots, and the only claim odd row is like starting on an even spot. However, in reality, like this is yellow to move. So as soon as yellow changes the parity of any of these rows, like if yellow plays in row 1, then immediately this claim even spot on an even row is exposed, and that is what the instruction sheet is telling you to do. Does that make sense?
Yeah.
I'll explain this in a little bit more detail in a second. Just give me one sec. So the next challenge is generalizing it. So I'll give you a hint of where I'm sort of going with this. If we end up being able to find a sufficiently dense amount of these positions that are describable by these simple steady state solutions, then we can use that as sort of a cap to cap our like opening book tree with. However, with just claim even and claim odd, it turns out to not really be enough. So we're going to need some slightly more complex notational rules to describe more behavior. So this is an example of what an actual steady state that like I have on my website will show you. Each of these pieces has their own sort of instruction associated with it. and those are inspired by sort of human Connect 4 strategy and like known play mechanics that are rather simple for humans to think about. The way to use this this sheet sort of said explicitly is what we're going to do is we're going to only care about the spots that are immediately exposed. Then we're going to sort of run a list of priorities against them. So in this spot, we would make a winning move if there's one available. We would block an opponent winning move if, like, this all makes sense. You want to win if possible. You want to block the opponent if possible. You want to play on an urgent spot if possible. So in this case, for example, if you're in this position and it's red to move, red would play here because this is the urgent mark. I think this is actually yellow to move in reality in this position. Actually, I forget. But if it were, let's just say hypothetically, if it were red to move, I think red would play here because the urgent is telling you to go there. You play on one of these two Miai spots if there's only one of them available. So in this case, there's two of them available, so you wouldn't want to play on either of them. However, if yellow takes one, we take the other. That's the principle here. Yellow takes this spot, red's going to take this spot, and vice versa. This is a Go term from Go, the board game, Miai. There's a lot of Miai in Go as well. Then rule 5 is the rule that we discussed already of claim even and claim odd. Play a claim odd spot if it's on an odd row. Play a claim even spot if it's on an even row. Otherwise, ignore them. Then play on a plus and equals a minus in that list of priorities. So you just walk through this list, looking at the exposed spots that you can play on, and you take the move that is in accordance with any of these, whichever is the first of these rules. Also, one thing I should note, it's kind of important to realize, like, from the rules themselves as written here, it's not necessarily the case that any suggestion is ever made. It's also not necessarily the case that a unique suggestion is made. So, like, the rules don't guarantee the uniqueness of a suggested move. But if you correctly design your steady state, you can force that to be the case. And for my weak solution and for all the steady states that I present here, I will be guaranteeing you that it always, in addition to always being able to guarantee you a win, it also guarantees you a unique move suggestion at any point in time. Okay, so let's try it. So just to make sure the mechanic here is clear, this is my website with the weak solution on it. So, like, I'll just click on a node here, and so now if we're playing as yellow, right? The agent is playing as red to demonstrate the weak solution. So imagine, like, well, where do you want to go as yellow? If you're playing as yellow here, anybody have any suggestions? Where would you want to play?
It's cut off somehow.
Oh, that's weird.
There we go.
How's that?
I think, yeah, it's a browser issue.
Okay. Where would you want to play? If you are yellow in this position, I'll zoom in a little bit.
So is this strategy for
Sorry,
yellow?
yellow's confusing. Yeah.
Say that again?
So what's yellow? Is that gray? Sorry, it's a bit confusing with the colors.
Oh yeah, sorry, the color scheme might be a little bit mustardy. Yeah, this is a yellow, this is a red. I think I took it from some, like, colorblind color palette or something like that. I don't remember exactly. It's not just, like, pure, like, RGB, like, max saturation yellow.
Is it either equal where the equal signs are?
You want to play where I'm asking you as yellow, right? I'm not asking you where you should be playing for, like, in accordance with the steady state. I'm asking you as yellow playing adversarially against red who is using this steady state. Where would you want to play? Just like if you're playing, there's no right answer here, right? Because we're going to lose anyway. Red's going to win. So where do you want to play? Just for a sample. If you don't pick, I will. I'll go ahead and say we'll start by playing on the second column. So if we play on the second column, where's red going to continue? This is now I'm asking you, using the steady state, what are we going to do? If yellow plays on the second column, where does red continue? Do you remember the rules? So there's no urgence, there's no red to win or yellow to win immediately, and there's no mi going on. However, this empty column is claim even. So if we play on the odd row, red's going to immediately follow up by playing on the even row afterwards. So that's the instruction that it's following. So if I play here again, what's going to happen?
Gonna add another one on top.
Yeah, bingo. Yeah, red's just going to keep claiming the even rows of this column. And like the same is true for the last column. If I play here, red plays immediately on top of it, and so on and so forth. So what's going to happen if I play this equals? How about that?
They're gonna claim even. Guessing.
Where are they going to claim? Well, this instruction says to claim odd, right?
Oh,
This row is saying you don't want to claim even here. You want to claim the odd rows.
so if yellow went there on the equal sign, red's gonna do something
Yeah, where's
else.
red going to go?
Red's gonna go on the other. Oh, they're gonna do that.
Red's going to go where?
A lot got filled in.
Sorry?
Did a lot of moves just happen?
Maybe it's lagging. Yeah, I played a bunch of moves just to illustrate the claim even happening. Yeah, so like red goes here. Like if red continues playing on these like empty spots, then you get like it exhibits claim even. It's just playing by claim even. But yeah, if red plays on the equals, then red doesn't want to play claim even on the claim even columns, like on this column and on this column. Red doesn't want to play there, right? Because this is an odd row and this is an odd row. So if red plays on the equals, the next highest priority thing is to play on the other equals, like this. These are functionally, in this case, these two equals are doing the same thing as mi does, right? If I play an equals, you play the other equals. But that's the idea. Is if I play here, then red's going to go there. Then if I go on this like vertical bar, red's going to claim odd after that. Hi, John.
So can you repeat? Yeah. Can you repeat what you mean by claim even, claim odd? Does that mean like you?
Yeah. So
yeah.
Yeah. So we're using claim even, and claim odd to mean a local instruction, like for a given column, where you should where you are going to play either like you're going to make the move on the even rows or the odd rows and ignore it otherwise. So for example, on this last column here, the odd circle is exposed, so red doesn't want to play there because this is claim even. So on the even rows, like if we play here, red's going to take the even spot because this is on row 4. Claim even is an instruction locally within the column to play on the rows that are even and not the ones that are odd.
Okay, so being the first row is 1 uneven, second row is 2 even, third row is uneven.
So we're talking about the exposed row. The exposed row here on column 1 and column 2 is odd, right? It's row 1 that's exposed on column 1, right? Column 1 is exposed on the first row, on the bottom row. The same is true of column 2. So the instructions are telling red to play on the even rows, not the odd rows,
okay.
the bottom
I thought it just mattered how many numbers of each ended up in the total row, but what you're talking about is the row number even or odd? Got it.
Yeah, is the exposed position that is about to be played even or odd? If it's even and the instruction is to play claim even, then you take it. If it's odd and the instruction is to play claim odd, or sorry, if it's odd and the instruction is to play claim even, then you don't take it, right? It's just telling you claim the even rows. That's the instruction.
So a question here. So is this just a heuristic that has been discovered from this weak solution, or is this a known thing that people play?
This is like just by observation, you can find it's not hard to find a good number of positions sort of like this one. Like you'll run into things like this occasionally in practice where like in reality you actually end up just wanting to do this. So it's a simple human solution that you'll probably find on your own if you're left to play enough Connect 4, and each of the other instructions sort of, a number of the other instructions follow the same idea. Sometimes there are just things that you want to do with high priority, things you want to do with low priority, and like things that you have to do immediately, and things that you like for example, the mi instruction, it actually kind of also corresponds to a sort of a formal rule that was discussed in Alice's paper called base inverse. That was his word for it. So like they're just common strategies that you want to apply, that you want to apply, and all I've done is sort of formalize that and put it into a notation for like for these sort of cheat sheet programs, basically.
And the overall motivation here is you could keep these cheat sheets in your mind at
Exactly.
the competition. Yeah.
Right, exactly. Right. So if we want to memorize the whole weak solution to this thing, we want to memorize the one that's on the right, right? This cheat sheet is a language that is expressing the regularity of this thing on the right with few characters in not much information. Does that make sense?
So there's more of a symmetry, so you can kind of
Right,
like
exactly.
duplicate it in more dimensions or something. Yeah.
Precisely. Yeah, yeah. It's a regular structure, so it takes less information to describe. Okay, so that's how that works. I kind of already talked a little bit about why each of the individual things was selected. A lot of it was just trial and error on my part. To be clear, I'm not making the assertion that this is the best language. I'm sure you could come up with others. I played with plenty of other ones, and it took a while until I ended up converging on this as sort of being a good middle point in between like computational expressiveness and simplicity. But yeah, they're very simple. It's fast to execute. You can interpret what they're doing if you look at a couple of them and get used to the notation. They reflect what you'll actually see in real Connect 4 and also what humans play. There's also the added bonus of, I say no search. You can nitpick on this a little bit and claim that the first two things are really search because you're like identifying if there's an immediate like an immediate win or something like that. But really, there's no unbounded search, right? There's no search any further than a depth of 1. So I call it no search. Also, there's the extra bonus of you can find these pretty easily with a genetic algorithm. There's no, like at first I was finding them by hand, but then I ended up, I had to automate the identification of these programs. And it turns out genetic algorithms are good enough to come up with these things on the fly. Okay, so what steady state solves the whole game? Of course, there isn't one. This doesn't solve the problem entirely for us. That would be too convenient. As yellow starts to insert more information into the board, you end up with there's less adversarial tricks available. There's less weird complexities that can come up as the position becomes more and more local, and there's more of a high chance that you get these super regular substructures in this weak solution graph. However, as I sort of mentioned earlier, if we can identify enough of these steady states, then we can like cap an opening book by these steady states, and thereby we can construct this really small opening book that satisfies all the goals of this project. So this is sort of a game. So imagine this is the whole weak solution tree of Connect 4. Or rather like the union of all weak solution trees. Let's say that this is the union of all weak solution trees of Connect 4. And I want you to find the minimal weak solution of Connect 4, as in the smallest one in terms of the amount of nodes. I'm notating positions that have steady states as these ones that have green slash marks through them. So can you try and find the minimal graph that satisfies all of the sort of invariant necessities of a weak solution? Yeah, can you find that minimal graph? You can blurt out the amount of nodes if you think you've got it.
So like trim this graph to make sure that you get to all the end nodes with the check marks on them, the green marks.
Right. Yeah, exactly. What's the smallest subtree of this tree that has for which each red node has one outgoing edge, but for all yellow to move nodes, there's all of the outgoing edges. What's the smallest subgraph that you can come up with that does that?
That's interesting. I would say like cut out the one on the left.
Well, isn't it like the left edge, more or less?
The left
No, but
edge.
You need all four of the nodes at the bottom. So you need the left edge and you need the middle one. The one on the right can go.
We're not trying to include all the nodes on the bottom. We want to find a minimal graph. We don't have to include all of the terminal nodes. The only requirement here is that we have like any yellow to move node has 2 outgoing edges, and any red to move node has 1 outgoing edge.
The smallest would be 6 nodes if you start to the right.
That's correct that you start to the right, but you can do better than 6.
Yeah, you can choose the same move on the second move. Then it's only 5. Yeah.
Yeah. So yep. So I'm assuming this is the one that you're looking at.
Yeah.
Yep. 5 nodes. So this is sort of like, this is just as an inspiration of sort of what the final challenge of this project is if you can identify these steady states, then how do you actually find this minimal tree? Now, to be clear, I'm not claiming that my tree is minimal. It definitely isn't. Every time I run more search on it, I end up cutting more and more nodes off. Just like 3 weeks ago, this was double the size that it is now. So there's certainly still some reductions to be made. But this is the idea, is, we're trying to cut off as many possible branches as possible. Sometimes also we're trying to make these transpositions such that, like, you can point at the same substructure from 2 different starting points. Lots of sort of little ways to optimize the amount of nodes in this final graph. As I mentioned, lots and lots and lots of search was used to find this. Sometimes, like, there were some people who reached out to me and were able to actually identify some steady states by hand and like cut down on graph size and stuff like that. Or also there were also people who said, oh, what if you try this variation instead? Like, I think this one's probably simpler than this one. And in many of those cases, they actually found something that ended up reducing the graph. But overall, just tons and tons of search.
But there's 2 different kinds of search, right? There's the search for the winning strategy.
Yes.
So the move choices, and within each leaf there is the search for the steady state.
Yeah, that's exactly right. Yes. So we have to do both. A lot of the time, we don't know up front which nodes have steady states and which don't. So that all has to happen on the fly. And there's sort of like, you can sort of explore branches expecting there to, like, not be steady states there, but maybe there are, and you don't know up front where to be focusing your search on. So
how complex is the steady state search?
It depends on the board. So in some of them, like, my genetic algorithm will reliably find them instantly. For more complex ones, sometimes it doesn't find them until, like, after an hour of just, like, re-roll and retry the genetic algorithm.
Wait, 1 hour for one position?
Yeah.
That seems like a really bad way
it
to spend
very
your
well
effort.
might be.
I would expect there to be some cutoff time. Like, if you don't find one in 1 second, then you give up on that node.
Yeah, that's exactly what I do. Yeah, to be clear, like,
Okay.
I'm talking about rerunning the program over and over again, and, like, probably like a collective CPU time of probably an hour is an overestimate. I'm not really sure, but I haven't actually timed the amount of like the distribution, like the spectrum of amount of time spent on different positions and how much time was spent finding their steady states. Because a lot of the time, like, you just want to move on. You just, like, if you don't find one within a second, it's probably good to just move on to the next one. And that's exactly what I did. I just did, like, a bunch of small searches with cutoff times. A lot of different types of searches as well. Like, a lot of the time what I was doing was, like, searching, for example, at a depth of 6 ply, like, just what's the smallest graph that we can find for any node. And a lot of the time, sometimes that would, like, end up switching the general strategy, or it would end up just finding, like, some new steady state that eliminated the need to even ask the question in the first place. So it all depends. Another search that I did a lot of was, like, sort of cross-pollination between, like, locally close nodes on the graph. Like, can we cross-pollinate their genetic algorithm starting positions with each other's steady states, such that hopefully they start with a better chance of converging on a solution. And that ended up being quite helpful as well. Lots of different types of search. Okay, so results.
Yeah, can you comment on the structure of this? I mean, it seems almost symmetric, except for like a little.
Yep. Yeah. We'll get there. Don't worry.
Okay.
I'll get there in a little bit. So, and yes, precisely. Yeah, I'll mention that now. So like, there's very naturally going to be a symmetry here because, um, in the board itself is symmetric, right? There's a left and right symmetry. So this spot here is the opening position, and you can either start by moving left or right, and that is precisely what's reflected in the graph here. Like all of these moves to the left are starting on the left, and vice versa. So all of the results I'll be mentioning here also are not accounting for mirroring. So you can shrink a lot of the sizes and things here. By accounting for those mirror positions. But we get 9,572 nodes as of right now. Just 2 nights ago we were at 9,800. So I'm with search and with suggestions from people online. I'm slowly reducing it. Last year I was up at like 1,000 or 150,000 nodes or something stupid like that. So still shrinking. Of course, the design decisions behind. Sorry, did my screen just change? I think Zoom's preview is like wrong on my side. Apologies. So comparing this to Victor Alice's paper, of course, our design decisions were very different, and I'll talk about this in a little bit more detail later. But like the sort of data product that he produced through his paper was a opening book that has 500,000 nodes. And even so, to play perfect play, you still had to do search on the leaves of those nodes. So it was fast enough for a computer to play in real time back in the 1980s, but like still a much larger product that you're interfacing with, a much larger program. Now, I won't comment on whether this is human memorizable. I'm sure if someone sat down and dedicated their life to it, it's probably possible, but this seems like a plausible in my book. Compressing everything, like serializing the data, we get like to have the information all just stored flat, so you can read from it. You get 300 kilobytes. Compressed, you get 167 kilobytes. Of course, this is a total apples to oranges comparison, but that's a 50 millionth of the strong solution size, so quite small. Also, as I mentioned, or as I showed just a minute ago, we can render this thing in real time. We can spin it around in 3D. Like visualizing this is no longer a challenge, and you can actually play with the nodes and really get a grasp of what's going on there. You can even move around on it and see like the variations that are continuations of what you're about to play. Rendering this thing is not challenging. I'm not even doing that on the GPU. That's all on the CPU anyway. So another thing that I was thinking about a lot of is like this. So validating this entire tree that I have here runs faster than 4 stones. Maybe John can comment on this a little bit, but I think my like tree validator is probably much slower than 4 stones. I did not optimize it that much. However, insofar as we know up front what branches to check and what to look at, and what what branches to ignore and not even bother reading into, validating the correctness of my tree it like runs faster than 4 stones does on the opening move. And in some sense, I think this could be described as like being a minimal proof through computation that Connect 4 is read to win. And in addition to that, I've one thing that I kind of have on my to-do list, I'm not sure if I'll get to it or not, is like these steady states can also be proven automatically. So currently what I'm doing here is like I'm still brute force reading through the entire steady state and like tracking transpositions. But other than that, there's nothing clever going on. I'm just brute force like confirming its correctness.
And
like,
the steady states are can you remind us again? They're board positions that, like, as long as you have this heuristic.
The steady state is the cheat sheet. It's the program that tells you what to do at any given node. So like even with this, like there's certainly ways that you could like prove this in an automated fashion, like prove its correctness in an automated way. For example, like the one that was like way back up here, like since this is so simple, like you can tell that yellow is like provably never going to ever make any moves that are not on the spots that I have yellow dots here. So like you can prove rather simply that yellow is going to lose and red is going to win without having to exert any search, right? But all I'm saying is this number here, this is still involving tons and tons of brute force search.
Right.
So may I suggest an experiment that might be interesting?
Yeah.
So if you go over your entire search tree of the 9,000 something nodes, and for each of them, you instead of checking your steady state, you run four stones on that.
I actually thought I was thinking the exact same thing.
I'm curious whether running 4 stones to verify those leaves is faster than checking the steady states.
Yeah, that's definitely an interesting thing to try. I thought about it myself too, actually, because like the question here is basically like, is it like 4 stones might be investing a whole lot of time into some like starting position that is like a starting variation that turns out to be wrong, or is it just like throughout the leaves of this big tree, it's distributing a lot of compute over like little tiny branches that turn out to be wrong. Yeah, so I'm curious. Maybe I'll try it out and let you know how that goes. But yeah, that's the idea. Okay, so going back to our little graph here, what have we done? We've sort of spit in its face and come under the curve by, we've still taken a sort of strategy X approach of memorizing a bit of an opening book. We can't do everything from the start. However, we've eliminated the need for on-the-fly compute. All of this stuff happens in like a very, very fast bounded amount of time. And, arguably, there's sort of a third axis here that I'm kind of hiding, which is upfront preparation, right? I've shrunk the amount of runtime compute by exerting a whole bunch of upfront search for these steady state positions. So really, it's somewhat hidden from this graph alone. But like if there's a third axis here, I'm jumping out of the screen quite a bit to in terms of just raw CPU time spent doing search to figure out this optimal solution that we can play in the first place.
Just looking at that graph for a moment,
Yep.
I'm curious about like the limits of human player ability, and do you think that at the current node count, like it is memorizable for somebody just to play it? Like
personally,
some genius. Yeah.
Like personally, I think if someone like were to actually like treat it as their full-time job, I think it's probably doable. But I mean, of course, there's room for debate there. I don't know exactly. You might get sick and tired of doing that for however many months. I don't expect anyone to actually go and memorize this thing, or at least not yet. Not unless I can reduce it quite a bit more.
And have you got some feeling of what the lower bound will be like? Like, how would you know that it?
Yeah.
Like, how small can it get?
Yeah. So there's sort of a trade-off between the expressiveness of the steady state language and the like the size of the graph, right? Because if I make the steady states even more expressive, then like we can shrink the graph even more. Expressive meaning like, for example, a very simple rule that I could add is like instead of doing that depth 1 search for winning moves, what if I do a depth 2 search, right? And then in that case, my hypothesis is this graph would be probably much tinier. In fact, at first I tried it without that rule, without the rule of search for a winning move and search for an opponent's winning move, and I had so much trouble even constructing the graph to begin with that I ended up just abandoning that, and I had to add the small depth 1 search rule at the beginning.
So would that be the equivalent of trading in some memorization for a little bit
precisely? Yeah, that's exactly right. Yeah, that's exactly the idea. Are we willing to spend more compute? Are we willing to permit more complexity in our language to reduce the amount of upfront memorization? So the answer to your question is it depends on what your goals are, right? You could change the language and make the tree a lot smaller. However, if I'm answering just on behalf of the current steady state rules as they are right now, my guess is probably this can be shaved down by a half. However, I have been very wrong about this in the past, so I don't know. 2 weeks ago, when it was at like 22,000 nodes or something, I was like, I think I wrote somewhere in my like little explanation document online that I think it can be probably shaved down by a quarter. But so far, we're already down more than a half. So take all of my words with a grain of salt. I have no idea. But yeah.
So just curious, is Connect 4 like still a competitive game? Like, is there like tournaments and stuff? Or?
Yeah, so yes and no. People play online somewhat competitively. There are people who claim to play optimally. I know of a number of people on Discord who have claimed to me that they play optimal Connect 4. I've seen one of them thereafter lose Connect 4. So, I don't know if any of their words should be trusted, but like, it is the case that a lot of people can play near perfectly, or at least can reliably play correct Connect 4 in most scenarios. So
it'll be interesting to know what they're doing then, if they're using like a certain set of heuristics, just
yeah,
raw intuition. Yeah.
Personally, I think it's very, very similar to what this graph is modeling. And I'll talk a little bit about openings and stuff like that in a moment. But yeah, I think like the steady state graph, at least to me personally, perhaps this is partially the reason that I came up with it, is because it's somewhat similar to the strategy, the way that I think about the game. But yeah, I think it models my intuition in many cases. There are a number of positions that have like other human known strategies. Like one's called like triple odds, where you create like 3 odd threats as red, and you get a way to force one of them to become real. However, as far as I've been able to find, there's no way to represent that with my steady state positions, because you sort of have to have a degree of like global awareness of the 3 threats at the same time. So it works for humans, but my thing doesn't seem to be expressive enough in showing it. However, as a whole, I think my language more or less expresses human intuition in most cases. And also, I think the graph definitely captures a lot of real openings that real human players care about. And I'll show you that in a little bit.
So yeah, a couple of questions from chat. Nightmare Court Pictures is asking if this graph is depicting the geodesics for shortest path to win.
Say that again. I didn't hear the word.
Is the graph like showing geodesics for the
geodesics, like geodesic curves? And no, the spatial representation of the graph itself is done by like a force-directed drawing algorithm. So basically, the idea is you treat each node as a proton that repels other nodes, and each edge is a spring.
Oh, yeah,
and then you just let the physics play out.
Spring electrical, I guess, is one way to describe that graph layout. But they're asking if it geodesic in the sense that it's connecting the shortest path to a victory.
Also, that's not the case either.
Okay.
I'm not making any guarantees, and I would actually be quite confident that there are plenty of cases in which we're foregoing a faster win for a simpler win.
All right.
As a matter of,
yeah, that's a good point.
Yeah. As a matter of fact, so like the Connect 4 solver that runs in browser, this one up here, that's online, it's a lot of people online are known for cheating using it, but usually you can quite reliably tell, because they'll do exactly that. They'll play these extremely complex variations that end in a faster win, but that no human would ever play under normal circumstances. So yes, this is something that comes up in practice, and fastest win is not the same thing as simplest win from a intuitive perspective. So I sort of mentioned this already, is like, we have this rather instantaneous runtime, but the drawback there is that tons of upfront compute was spent. In addition to that, it's a weak solution. I cannot make any comments on anything outside of this graph, right? And I also can't say that it's optimal. And also, like, early move suggestions were made by human experts as well as myself. So I also cannot guarantee that it was anything computational in nature that guided those decisions to be made, other than human expert player intuition. So they might not be optimal. I don't know. Okay, so actually discussing the structure of this thing itself. So what's going on anatomically within this graph? This is the empty board. You already kind of mentioned the mirror symmetry, although what about this? Any ideas as to why there are some slight asymmetries in it? It's not because I screwed up, I'll tell you that.
Just remind us, is there an even number of columns? Uneven.
It's an odd number of columns. It's 7 wide, 6 tall.
This should make no sense then.
It does make sense. In fact, you can actually show that they're necessary. In fact, the intersection of all weak solutions will exhibit the same asymmetries. Shall I spoil it?
Yeah, I can't think of what.
These they come from when red is forced to make an asymmetric decision. For example, like if we fill up the whole column, which so like in this game, all of these moves are actually forced. So this is a necessary thing that has to exist within our graph. If red fills up, or if we fill up the whole center column in this way, red is forced to make an asymmetry themselves. So we choose in the graph to play on the right side. This is an arbitrary choice, so we're playing on the left side. But we don't need to memorize what happens if we play on the left side, because we're just going to play on the right side. This is just one of them. This just happens to be the easiest one to see visually, I think. There's like another few asymmetries up in what I call the crown here. Yeah. But yeah. Okay, so let's go ahead and
like why isn't that same blob reflected on the other side?
Well, so precisely that. So like insofar as we fill up this column, red's going to select the move on the right. Red's not going to select the move on the left because we only have to memorize one continuation. We're going to memorize the right continuation
up to
just up to arbitrary choice.
Because we want to reduce the number of total nodes. So why would you leave? Yeah.
Yeah. Why would you memorize the side where red chooses the left instead of where red chooses the right?
Because it's going to be the same outcome. So you want to just cut out half of. Otherwise, you're duplicating the number of nodes. Yeah.
Yeah. Exactly.
Okay. Yeah. JN from chat mentioned that. Was asking about isomorphic configurations being. So yeah, so you're pruning out the thing based on isomorphism sometimes.
It's more so just like the entire algorithm is designed such that red is making one decision. Red just has to make one decision. That's all that the rule says. So insofar as red makes one decision, a decision is forced. You have to pick one of the two asymmetries.
Okay.
It's just up to arbitrary choice.
Got it.
Cool. So, okay. So I figured I'd actually talk about the actual anatomy of this thing a little bit. So, and so one thing that has to happen here actually up to entirely forced moves by red is an opening called candlesticks. This is not my name for it. But like this continuation, every move so far in this game has been forced for red. So in fact, you can say that this exists in the intersection of all weak solutions of the game. So it has to be in our graph somewhere. And this whole crown basically corresponds to variations that are somehow leading up to or continuations of candlesticks. So this totally in line with human player intuition and named openings and things that people already know about the game. And also it's forced to be there. Like we know, like mathematically, that this whole thing has to be present because every move is forced. In addition to this, okay, so there's a lot of interesting openings that come out of if yellow plays here, then I mentioned like these two positions are both options. And this was an example in which I had to defer to like human intuition. By Connect 4 wisdom of humans, this is considered to generally be the better move here. So that's what we went with. And that leads to all these variations on the left. One of the big ones, this is sort of one of the really tricky openings, is this thing here, which leads to this big arm. I call this one of the arms of the graph. Of course, the mirror symmetry just explains the other arm. So all sorts of complexity that jumps out of this thing. These little nubs at the bottom here correspond to what happens if yellow plays on the edge. It makes a lot of sense that playing on the edge doesn't really help much, just insofar as there's not many lines of length 4 that emanate from this position, right? You've only got like this diagonal possible and this vertical possible. So this sort of just intuitively doesn't seem like a very good move. And that's reflected in the graph of this being a quite concise and small definition required to play perfect play after this left move. And like all of the other moves here basically correspond to first, like these, I call them like the tentacles. These all correspond to like first row openings, where, you know, yellow plays on the bottom and like, you know, something like this happens. Those are first row openings. So these all correspond to like things that humans study in practice. All of these little lines, like if you come up to an expert Connect 4 player, they probably know these lines by heart. Like a lot of the little like a lot of these little sort of one-off variants here that you'll see, like this line here. Like there's a number of these, and they correspond to actual just sort of forced complex lines that that don't evoke tons of complexities, but you just sort of have to memorize the way that it goes out as an opening. Yeah, and that's basically the graph. I could ramble about like little some of the anatomy for all day, because like this is a common position. Like the position that I mentioned earlier, the one where you fill up the whole column, like this is common. This is called the 6-1, because like there's 6 in the middle and then one off, and there's like the wide and the narrow 6-1. So if yellow plays here, this is the wide 6-1, and that's the asymmetry that we had over here, right? This is very common online. If you play online on like beginner servers, they'll definitely play this, and this is all you have to memorize to play perfectly here. So if you want to go and win like 90% of your games online, just memorize this.
Is there a dictionary or like a library of these moves with names?
Not that I'm aware of. So James Dow Allen, the guy who solved the game first, he wrote a book, and he discusses a whole lot of these variations in a lot of the openings. So there's that. But other than that, I'm not aware of any list of names, other than just like from talking to people. Cool. Yeah, so we talked about the openings a little bit. What else?
Let's see.
So I also kind of wanted to...
Can you speak to the symmetry of this graph? Is it everything on the left is like a mirror image of everything on the right and the board state, or is it more combinatoric than that?
Nope, that's exactly right. Yeah, it's like if I click on this node here and this node here, they're mirror opposites.
Oh,
Nothing surprising going on. So
technically, could you prune this down to like a half based on?
Yeah. All of the metrics that I've been mentioning so far, you can prune by slightly less than half because of the asymmetries and the openings that involve like a middle row only. Like those nodes are going to have to be there anyway because there's no mirror for them. But like, you could cut this down by almost half by eliminating mirror symmetries. And
but that would be up to your opponent, right? You wouldn't be able to choose which half you go down. Is that?
You would have to you'd have to mentally flip the board in your mind. That's. But like in principle, there's nothing stopping you from doing this.
Tolga was asking about rotational symmetries. I kind of stepped in and said that like since this is a gravity-fed game, like the bottom has to be the bottom, so only.
Right. Yeah, exactly. You're not going to get a vertical symmetry because you can't have pieces floating on the top.
Yeah.
Yep. What else? Yeah, so I also kind of wanted to just mention in brief, I know you guys think a lot more about algorithmic information theory than I do, so this is partially a question to you, I think. Like, I'm sort of going against the grain from an algorithmic information theory perspective here because, the simplest program that you could write to play perfect Connect 4 would probably just be plain minimax, without any complicated awareness of strategy, right? But the thing is that then is you abuse compute. You have to do tons of search. So like in some sense, I think this is not quote unquote the good way from the algorithmic information theorists' perspective, and sort of along the same line, like the left object here, the strong solution tree, is extremely computationally reducible, right? Insofar as it can just be described by plain minimax. However, my object on the right here, like there was choice involved, there was human choice involved, there's entropy that's been introduced by arbitrary choice and stuff like that. So in some sense, this is more computationally reducible than this one, which makes me which makes me think, because like intuitively the right thing is a simpler object to me than the entire complexity of the whole board, the whole game. So which is kind of why I was thinking a little bit earlier about like validation runtime. If we're iterating over this tree, how long does it take to validate the correctness of our tree? That sort of is a way of formalizing the idea that like our ability to not make excessive use of compute to validate our program is a way of thinking about this sort of apparent simplicity.
Well, that's a theme in algorithmic information theory, that to find the very simplest things takes a lot of resources, and then in the limit you run into the halting problem. To find the totally simplest thing, like the combinatoric complexity of something, that's not even computable.
Right. Yeah, so I don't know. Is this a metric that people actually use in practice? I'm not sure. Is there an equivalent or something similar to like this validation runtime idea that you're aware of?
No, there's not many games that have this feature of steady states. I think.
Are you sure? I think that's a bit of a more incredible claim than on the surface. Like, I mean, of course, the language wouldn't map one to one, but I think there might be, I think you might be able to play similar tricks with other games. I'm thinking about applying the same thought process to Othello at some point, although I don't know how to do it.
Well, certainly, Victor Alice's thesis is the first,
right,
and one of very few examples where a game is solved by finding little proofs.
Right.
On leaves of a tree.
Yes.
And I think games like Othello were solved in a more brute force manner.
Right. Yeah. The nice thing about Alice's solution is like he's able to prove things generally, whereas my language here is entirely position specific, right? So I think although that sheds more light onto Connect 4 as a whole, maybe like I think insofar as my language is position specific, I can be a little bit more expressive about certain positions and how continuations of them would look. And I think that philosophy would map more easily onto Othello. For example, the mere idea of like having a plus equals minus symbol priority list would probably describe a number of endgames of very small, like short, like maybe 3-ply endgames of a whole bunch of different games like Othello or something.
Of course, Victor was motivated in a different manner. He wanted to find the value of the game, and he actually thought initially that it should be a 2-player win, and that's what he was trying to prove. And when that became harder and harder and harder, he at some point judged that that means if I cannot prove that it's a 2-player win, then it has to be a draw. So let's change my my project to become proving a draw. And again, he worked very, very hard and kept running into difficulties. And only at a very late stage did he ponder the possibility that it might be a 1st-player win.
Yeah.
But he didn't at that point when he got that result that it was a win. He didn't care about optimizing his proof systems anymore.
Yeah, exactly. Yeah. Also, one thing that was pretty cool when I was developing this graph, I would say most of my like the branches that I found like correlated with the ones that his program identified, or at least the ones that he mentioned in the paper as like as the simplest continuations. Most of them agreed. There was however like one chance in which they disagreed, and I ended up trying his, and his actually did turn out to be, I was able to reduce the graph that way by actually just deferring to the suggestion that his paper made. Although I had to do a whole bunch of search at, like, again after the fact. But so that was pretty cool that we ended up converging on 100% agreement on, or at least from what he wrote in the paper. I don't know about other than that, but all of the design decisions mapped 1-to-1. Yeah, so who cares is the question that you might ask. Like, these emergent objects are everywhere, and if we want to think about them and we want to avoid this brute force search that requires no deep understanding of what's actually happening under the hood, I think methods like this are kind of necessary. You have to start to identify regularities in systems and understand what's actually happening under the hood from a sort of articulable perspective, and start to come up with languages that represent substructures within the object, and this maps onto a lot of the other topics that I discuss in my channel, where you have this, this system where you iterate it, maybe, or you just have rules at the atomic level, right? There's a rule that defines the win condition. You abstract a little bit upwards, and you get this rather well-behaved local structure, and you abstract much further, and then those slight local inconsistencies and quirks compound on each other, and you get this much more complicated entropic object that emerges as a whole, which is totally resembling all of the other stuff that I discuss in my channel, and also precisely what you guys think about as well, with physics at the absolute bottom being simple sets of rules, and at the highest level we see all of this emergent complexity as a result. How do you understand it? I think a little bit of this has to happen. A little bit of how would I say, identification of substructure and rules has to be a part of that approach. Cool. Any questions? That's all I have.
With this analysis that you have, probing into this combinatorial multi-way graph, do you think new heuristics could be gleaned from it?
Heuristics in Connect 4, you mean?
Yeah.
Or heuristics for human play, or like heuristics
sure.
for search?
Or like a computer found heuristic, for instance.
All of the above. I think, yeah, I can think of several things in either case. Like, I mean, just being aware of like the fact that these MII spots are a thing, and being aware that you should be looking out for positions in which there's an even amount of empty spaces in each column. This is super helpful in real Connect 4 play, in my personal experience. Like, if you can just identify those, it'll give you a sense of what to look for and how to force these very, very simple wins later on in the game. And I think that could also be applied directly to computers as well. I think heuristics like that, and just being able to quickly scope out, like, is it even like theoretically feasible that this could just result in claim even? That could certainly accelerate search. Probably. I don't know. I haven't tried it, of course. Maybe brute force would just be faster, but it seems like something to try. Yeah.
So for people doing optimal play, quote unquote,
yep.
Some people claim to. So I mean, I guess the test is, do they win every time if they go first?
Yeah. In practice, the people, like, I know people who I would bet like 100-to-1 odds that against some randomly selected agent they would win.
Mm-hmm.
I think I would probably bet 100-to-1 odds against, if they were playing against some omniscient being who could like read their mind. I'm guessing they probably wouldn't always win.
Well, I mean, the omniscient being would just have to memorize this 4 terabyte, game tree, or.
Well, I'm saying even beyond that, an omniscient being who understands their mental model of the game and can exploit it. I think, like me personally, against that solver that I showed at the beginning of the game, I don't know about now. I haven't actually seriously played Connect 4 for like a year or two, but like back when I was playing it a lot, like I could pretty much always win against that solver that I showed at the beginning of the game, or at the beginning of the presentation.
Yeah, yeah.
So what you said about if you were to play against a perfect being,
Yep.
and what if they were trying to take advantage of you? I think that's
Right.
nicely paraphrased in some discussion with Go players about how
Yeah.
much handicap do you think you would need against God?
Right. Yep.
They might say 4, and then
I
but
think
if I
it's
were
more
playing,
than 4.
but then they would need more against when they were playing against the devil, where the devil is not restricted to optimal moves. The devil will be happy to
Right.
play some optimal moves
Yes.
if it thinks it can make you
Right.
blunder even
Yeah.
worse.
Yeah. With contempt, you can get even more expressive in your ways of messing with the opponent. You didn't ask, but I personally think like Shinjin So would probably take like more than 4 stones from God, but I'm not sure.
Definitely more than 4 against the devil.
Yeah. Sorry. I meant to say against the devil, but
Yeah.
against God, unless yeah, I don't know. But yeah, thanks a bunch. Any other questions?
Yeah.
Also, thanks to you, John. I'm glad you joined because like I 4 stones, I didn't mention it, but like 4 stones was used very intimately in evaluating positions under the hood when I was constructing my graph. So this very much wouldn't have been possible without that. Also, thanks to all the people who chimed in and messaged me on Discord and sent me branch reductions on the graph. Got a whole bunch of those. And thanks to you guys for having me on.
Absolutely.
Thank you very much.
Yeah, I appreciate it.
I have one more
Totally.
suggestion to make. So if you were to do your project of a minimal search tree,
Yep.
a minimal winning strategy based on 4 stones results, what you could do is take those some, I think, 65,000 8-ply positions that
Yeah.
4 stones has evaluated,
Yep.
together with the weight, which is an indication of how hard it is to win from there. And you could try to find a minimal weight winning tree that has all the leaves at those 8 plies. Given those weights.
That was actually the first approach I started taking.
Okay, so I think if you do that, you must also end up with a winning tree that is on the order of a few thousand nodes.
Maybe I wouldn't.
Most of those 65,000s are going to be irrelevant to the winning strategy.
Wait a minute, maybe I misunderstood. You're saying look at the 8-ply database, then cap the tree with what exactly?
Well, the 8-ply database just caps the tree at 8 plies. But for each of those leaves, it knows the theoretical result and how much effort it took 4 stones to determine that result.
Oh, you just mean plot the tree of like the weak solution tree or the smallest weak solution tree that results from that 8-ply database.
Yeah, but more specifically, the minimal weight.
The minimal weight, right? The minimal
subtree that minimizes the sum of the weights
of the leaf weights
that 4 stones determined. Yeah, so that you expect the overall or the average 4 stone search time from any leaf to be minimized.
Right. Is that published with the dataset?
No, that hasn't been done yet, but I'm suggesting that would be an interesting research topic.
Sorry. By published, I mean has the
the database has been. Yeah, the 8-ply database has been published, at least with just the theoretical outcomes. I don't think the work factors have been published in there now.
Gotcha. Okay.
But those are easy to just reproduce by running 4 stones again from scratch.
Yeah.
It doesn't take that long to produce the 8-ply database.
Right.
And then the resulting win strategy going up to 8-ply could be compared with your strategy up to 8-ply. Those must be pretty similar graphs then.
Yeah. I might do it. I might not. To be honest with you, like one of my big goals was to get it under 10,000 nodes, and I finally did that. So I'm kind of like, I've spent a long time on this, so I'm kind of burnt out a little bit. But maybe I am definitely going to turn this into a YouTube video. It'll be my next one. So maybe when I start doing that, I'll get back into it, and at that point, I'll do some comparison versus like your data set. Maybe if I can find Alice's data set, I'll take a look at that too. Yeah, I'll think about it.
Okay, thanks. Looking forward to it.
Yeah, I
There's
appreciate
a lot
it.
of people
And thanks for coming.
watching who might be able to help contribute on that. So how would they, if they wanted to help you to get to know it lower?
If you think you've identified a steady state on the graph, send it to me. I can verify it pretty easily and add it to the graph. If you think you've identified a whole branch that could be changed, I would need a little bit more justification because it takes a lot of work with search on my behalf to go and like, flush out that branch and confirm or not confirm, or maybe not confirm, but justify with a bit of statistical evidence that it's probably going to be smaller than what I've already got. So yeah, if you have suggestions, feel free to send me a message on Discord. I'm just TwoSwap on Discord. Yeah.
Awesome. I think Brian had a question as well.
Well, more comment, a little out of school comment about this. Many years back, Danny Hillis and I worked on something really similar that was about 1/47 millionth as hard. We did an analysis of the tic-tac-toe game tree in order to build a machine out of wood to play it.
Oh wow!
And when we were doing the game tree, the last optimizations that we did, which I don't think is I don't even know if it would work in your case, is we just looked at the nodes and looked at the transitions and assumed that if there's any place where you can take advantage of don't cares, what that did is it reduced our final tree by a factor of 3 or so. But
don't care as in meaning like you can like any move is winning.
No, it's you don't really care whether it's this particular thing was X or O or empty. Okay, it was basically the transition. Yeah, the transition was it triggers on these being present. We don't care about the rest of it.
Right. Yeah, I thought about combining like nodes in the graph that have like maybe like there's one node somewhere that's like completely blocked in all directions and it can't make a line of either color or things like that. But I ended up just deciding that like just the complexity of adding that and just the more like making the graph more confusing to understand in the first place was.
The thing is in our case, without that optimization, we had 430 some nodes, which was not realizable in wood. And with the optimization, it got down to about 140, which was realizable. So it made us happy.
Gotcha.
So two other minor comments. If you think that there are people who can actually play optimal games, have you actually tried doing what you're doing on the yellow side to see if you could beat them?
What do you mean doing what I'm doing on the yellow side?
Like just figure out the optimal yellow strategy.
Yeah, so you can so using the graph here, using the graph here, like you can take a simple metric of like yellow's best move by just like comparing like how big is the remaining graph after after I make my next move. I'm actually not even sure what it is in this case, but like, and you also might want to discount like mirroring, It's like maybe it's this, maybe this is the hardest opening by that metric. And maybe you could get smarter than just doing it greedily, like at a depth of one ply. Like
right. The thing that I was asking is when you're showing us the graph, you were only working out the graph for a particular red move, but for all yellow moves. Okay, that if you instead like do the whole process, assuming that you're yellow, red moved in its optimal first place, and then you pick one yellow move and then play out the possible red moves. Right. So rather than building.
Oh yeah, you're saying at each incorrect. Wait, are you talking about incorrect? Like red makes a mistake?
Well, it's just if you currently built the optimal red player. You could analogously build the optimal yellow player to tease the people who claim to be really good at it.
Well, is there an optimal yellow player? That's kind of what I mean here is like, how are we defining optimal yellow player? Because like, we could take optimal yellow player to be the agent which just preserves the most nodes still available on the next move or something to then hopefully hone in on like this variation or something like that. But
I think you're right that the optimal yellow player would be a subset of the work you've already done. But since it's already past the end of time, could I just one other suggestion
Sure.
is has anybody invented Connect 3?
On a 6x7 grid, you can force a combinatoric win immediately if I'm not mistaken, like within like just a couple moves.
Okay.
Yeah.
Okay,
But
because I was just thinking that the presentation that you're doing, if
Mhm,
there was a game where the numbers weren't so astronomical to begin with,
mhm.
it may make it easier to explain.
Yeah, I did think about then going back and doing this once again for like a 6x6 and like smaller boards, or rather only smaller boards that have either player one or player two to win, because a lot of the philosophy that went into this doesn't apply if it's a tie under optimal play, which I'll leave that as a I'll leave that as a problem to the listener to figure out why that's the case. But uh like yeah, I thought about going back and applying this
Just to
to
show the Connect 3 solution, like if it's very small, and then go Connect 4.
yeah, that could be done. I think it would make more sense to do it with a smaller board on Connect 4, because I think Connect 3 is like it's literally just a path. Like you can force the win pretty quickly.
Oh, it's a single part. That's okay. I see.
Yeah. Like you can like there's like 2 branches at most, I think, and everything after that is something like that. It's something stupid simple. I don't remember exactly what the tree looks like, but it's like you can immediately force a win.
Very cool.
Sweet. Thanks a bunch.
Yeah.
If I may
Appreciate it.
ask
Go ahead,
one more
Tom.
question.
Absolutely.
Let's see. In your overview of your rules, you had first make a winning move if you have one, and then number 2, block a winning move by the opponent if he has one.
Yes.
Those 2 are also part of Fourstone's move generator.
Okay.
But that has one more rule. Namely, it tries to enumerate all the moves it should consider playing, like in the move ordering. So the third rule is that do not play in a column if that allows the opponent to win right on top of it.
Okay, yeah, that makes sense, of course.
So that reduces your number of move options, and then it does the move sorting. I'm wondering if you introduce that as well, so you forbid some of the moves. Maybe you don't need 3 different levels, 6, 7, and 8 at the end, because maybe you only end up needing the minus to prevent some of those stupid moves. That could be instead forbidden by making it explicitly impossible to play where the opponent could win on top.
That could be.
So that's something you might want to try out, just to see if you could reduce the number of symbols used in your steady states.
Right. Yeah. That sounds like that makes sense. Yeah.
Okay. Thanks again for a wonderful
Appreciate
presentation.
it. Thanks for coming.
My pleasure.
Thanks to the Wolfram Institute for having me. I really appreciate it.
Thank you so much, TwoSwap, for taking the time, and thank you, John Tromp, for chiming in.
Yeah.
Appreciate it, and thanks to everyone tuning in on the live stream. Thank you for your questions.